Welcome to the course on fundamentals of MIMO wireless communications. We have discussed channel capacity, and finally we have arrived at the point where we are able to understand the capacity of a MIMO channel for a deterministic flat fading channel. So we need to now move forward and see different MIMO configurations and find what is the expression of capacity and what does that lead to. So when we look at MIMO, we have drawn this picture several times before, indicating a MIMO system. That means this is the transmitter, and we similarly have receivers with multiple antennas. And we have indicated that there are MR is the variable used for indicating number of receive antennas, MT is used to indicate the number of transmit antennas, and H is the channel matrix, which is of dimension MR cross MT. So we have done all these expressions. We have also looked at the expression of capacity. Now we need to look at two different configurations. One of the configuration is when there is no channel state information available at the transmitter, and the second situation is when channel state information is available at the transmitter. So the first case, when there is transmission from the source to the destination, it is all in this direction. And as it was said in the previous lecture, the channel H will be assumed to be ideally estimated, ideal estimation. Or perfect channel knowledge. So this is one of the first situations, and this is usually analyzed under the case known as channel unknown at the transmitter. The other situation which we'll encounter after covering this is when the channel which is ideally estimated at the receiver is fed back to the transmitter. So this is the next situation which we are going to analyze. So as of now, let's begin with the case when there is transmission from the source to destination in one direction. So when this is the situation, we have the signals S1 to SMT to be transmitted from the source, and since there is no knowledge about what's lying out there for the transmitter, therefore you cannot do anything with these symbols. Nothing can be done with it. So since there is nothing that is known, so in other words, we usually say that there is the channel has no preferred direction. Right? It is not specific to certain directions and is completely unknown to the transmitter, and therefore the vector S, which is composed of S1 to SMT, right, SMT, you cannot do anything with it. You cannot specifically modify this. So the best non-preferential thing that you can decide for this is to make RSS is equal to I of MT. RSS is basically expectation of S times S Hermitian. So S times S Hermitian, S is a vector and S Hermitian is a row vector. So when you take the product of it, it becomes a matrix. E of SS is basically the expectation or the covariance matrix of S, and we will ensure that E of S is equal to 0. That means it's 0 mean. So when you have E of SS Hermitian, we also have E of SI Sj conjugate is equal to 0 for I not equal to j. That means independent. So we are taking independent symbols in these cases. Therefore RSS is identity matrix, that is it has 1 0 0 0 0 and like that. So that will be the RSS. That means the signals are equi-powered and they are independent. at the transmit antenna. Okay. So, this is the primary thing which we take into account. So, when we look at the expression of capacity, which we had done in the previous lecture, capacity of a MIMO channel, of course, we are doing in the case where channel knowledge is not available at the transmitter, we would write C is equal to log of the determinant of I m r plus E s upon m t n naught h Hermitian. So, when we write a small h on top, it is the Hermitian and not the channel. So, it is not h raised to the power of h. So, this expression we had derived in the previous lecture. So, whatever things we do, it will be based on this particular expression. So, now we say that H Hermitian, this is a Hermitian matrix, it is a square matrix, it could be factorized into Q lambda Q Hermitian, where Q are orthonormal matrices and lambda is the diagonal matrix made of the eigenvalues of H Hermitian. And we also have the property that Q Hermitian is of I m r, right. So, in that case you could rewrite C as log determinant of I m r plus E s upon m t n naught Q lambda Q Hermitian. So, this is just doing the substitution of H Hermitian is equal to Q Hermitian. Using that, we have got this new expression. So, now we will be using the identity, the matrix identity, that determinant of I m plus the product of the matrix A and B could be set equals to determinant of I m plus product of the matrix B times A. You can take A to be m cross n and B to be n cross m, right, because we have H Hermitian. So, if we have it in this format, then yeah, so we will take this, and we also have Q Hermitian as I m r. So, this is already given over here, Q Hermitian is I m r, and if we have A is equal to Q, suppose I set A is equal to Q and I set B is equal to lambda times Q Hermitian. So, suppose I use this in the expression above, what I would get is Q lambda Q Hermitian could be written as lambda times, so we could write it this Q lambda Q Hermitian, you could write it also as lambda, because if this you would identify to be A and this you would identify to be B, then you could write it as B times A inside the determinant. So, if it is inside the determinant B times A, so you are going to get lambda times Q Hermitian. So, if it is lambda times Q Hermitian, Q and Q Hermitian is equal to I. So, basically it will be left with the lambda, and so basically this H Hermitian gets converted to Q lambda Q Hermitian, which can be written as lambda, because we are finally taking the determinant of it. E s by m t n naught remains, there is no change to it, plus I m r remains, there is no change to it, and you have determinant log base 2 as the expression of capacity. So, this is the new expression of capacity. This is nothing but from H Hermitian we have taken this factorization, used an identity and modified in this form. So, now when we focus in this particular expression, what do we see? This is a diagonal matrix 1 0 0 0 1 0 and so on. What is this? This is, you could write it as E s by m t n naught plus lambda 1 lambda 2 up to lambda r or lambda m, if we take m t equals to m r. So, that means we have a sum of two diagonal matrices which will again be a diagonal matrix with the elements as Es by mt n naught times lambda I. So, basically this will be a new diagonal matrix with these as the diagonal entries. So, we are taking the determinant of a matrix. The determinant of a matrix is basically product of the diagonal values, product of the eigenvalues. Determinant is equal to product I equals to 1 to mr times lambda I, or rather we should say r, where r is the rank of the matrix. So, we could rewrite this expression as C is equal to sum of I is equal to 1 to rank of the matrix log 2 of. So, you could put it as a product. Okay. There is an intermediate step. So, we have already skipped that step because it is a product of these. Basically, the intermediate step we have is log 2 times product I equals to 1 to r 1 plus Es by mt n naught times lambda I. So, this is what we have. So, log of product is equal to sum of log of individual terms 1 plus Es by mt n naught times lambda I. So, where r is the rank of the matrix and lambda i's are the eigenvalues of H Hermitian, and all these lambda i's that we are taking are greater than 0. So, we have this as the final expression of capacity for MIMO system, where a channel is not known at the transmitter, and we have arrived at by making certain assumptions that RSS is equal to I of mt, and H, of course, it is a standard notation that we have used. So, if we have if we take careful look at this particular expression, what can we say about it? So, when we take a look at this expression, we can say that the capacity of a MIMO channel, this is very interesting, capacity of a MIMO channel you can say as a sum of r number of CISO channels, each having power gain lambda I equals to 1 to up to r, and transmit power Es upon mt. So, when we look at it, you see this once again very carefully. We could write it again, log base 2 1 plus Es upon mt by n naught times lambda I. So, this clearly is expression of capacity of a single input single output system, where Es upon mt times lambda I you can say is the signal power, effective signal power, and n naught is the noise power. However, when we have MIMO links, this becomes a sum of I equals to 1 to r. So, that means it is a sum of r CISO channels having a power gain of lambda I. This is very fundamental. So, what basically MIMO gives you? MIMO gives you r parallel CISO links. So, as if between these antennas, as if when we have these two antennas, when we have these two systems, we can say that as if there are parallel CISO links. And how many of them are there? There are r number of parallel such CISO links between the transmitter and receiver, and each having a gain of lambda I, and the transmit power of each of the links is Es upon mt, and each of the links is experiencing a noise power of n naught. So, that could be the description of what could be the MIMO capacity of a system. So, what we have fundamentally achieved is whatever is the capacity of a CISO link, if we add r of them, where each of them has a signal strength or a strength of lambda I corresponding to the eigenvalue of that particular link, and each of the channel is excited by Es by mt, that means a certain fraction of the total transmit power, and we add up the capacities, we get the capacity of a MIMO link. So, if we So try to understand this expression, the implications of this, we'll get a better feeling of it. So if we do not have this summation, we would have had log base 2 1 plus Es by n naught for a seesaw link, and of course the channel coefficient would be there. So such a link, if I would make Es upon n naught on this axis, the capacity increases like a concave function, and we were operating at some point Es, but what has this done is it has made Es upon mt at this point. So this is, let's say, Es upon mt. It has reduced the SNR. However, it has added, so if this is the point, it has added r of them. So if I roughly speaking, if I would say this is the logarithmic curve, we have not drawn to scale. So there are 2 units, 1 plus 2 plus 3, so and so on and so forth. So what we clearly see is that in a seesaw link there was logarithmic increase in capacity, log base 2 1 plus Es upon n naught. So as Es would increase, there would be logarithmic growth, whereas here the capacity has grown several folds because we are adding it up. Although we have reduced it over here, in this part of the log function there is a linear like approximation that can be made for the log, and we are adding them up. So there is significant improvement in capacity, and there is, so basically there is some kind of a linear increase in capacity that you can say. And as you increase Es, so Es upon nt, it's not simply logarithmic growth. So this grows along with that, there is a summation, so which basically describes that there is a linear growth in capacity for such systems. So now what we will be doing is such a channel, we would like to see the given such a system, we would like to see that what is the configuration of these channel coefficients, or what kind of channel properties would lead to the best capacity that can be achieved. See, we have to try to understand that these expressions include lambda i's, right, and basically lambda i's from H Hermitian. So what we are trying to say is what properties of H would lead to the best value of C, because this is for a given set of H. If it is for a given set of H, then C is a function of H. So if H is random, C is also random. We'll see those things in details, but as of now we are trying to find out what property of H would lead to maximum value of C, right. So to do that, we'll consider that let us be given a fixed total channel power indicated by Frobenius norm squared of H. This we have studied, that is the sum of the elemental squared values, and this could be set equal to the trace of H Hermitian, which is sum of all the eigenvalues, and let us say this is equal to some constant zeta, and that is the given total fixed channel power. So that means channel has a total power which is not changing. So we'd like to find what is the nature of H, what is the nature of H that maximizes capacity. Okay. So when we are talking about this, to make life simple, we will make the assumption mt is equal to mr is equal to m. We will keep this assumption so that we get some easy results, and as we have said in the beginning that we are interested in getting an insight into the system. To get an insight, it's not necessary that we look at very complicated expressions, but it's important the expression gives us a meaning. So to get some easy understanding of things, we'd like to have mt equals to mr equals to m. For mt not equal to mr, results would be slightly different, but the meaning would still remain the same, and hence we take mt equals to mr equals to m, so that our expressions are more meaningful. So with this, and therefore we would assume that we will also assume it is a full rank. This also helps us in our looking through the expressions. So therefore the r is equal to m. So we use the expression we arrived at in the previous discussion, is that capacity equals to I equals to 1 to r, which is equal to m times log base 2 1 plus Es upon mt n naught times lambda I, right, and this is the expression we have. So, this is concave in variables lambda I, because we have described concave and convex functions. So, this is a concave function, the value of the function is above the chord. So, this is concave in lambda I, and therefore, we can say that this is maximized subject to the constraint which is given here. Subject to the constraint I equals to 1 to m lambda I is equal to zeta. So, we want to maximize this subject to this constraint, and it is a well known result, one can prove it also, will not digress to that particular outcome right now, is that lambda I, when lambda I is equal to lambda j, that means all the lambdas are equal, that is each of them is equal to zeta by m, this expression is maximized. Okay. So, that is a well known result which we will take advantage of. We will not go into further derivations, because that is going to take some additional few pages, and I would recommend you to take a look at it, otherwise this can be shown. So, this is a result which we have. So, this in turn indicates that this is maximized, that means capacity is maximized. When all the lambdas are equal, and that happens when H is a orthogonal matrix. We'll show it in very quick steps that why H orthogonal should lead to all of this, because if H is orthogonal, H Hermitian should be equals to H Hermitian H should be equals to a identity matrix. So, I have I of m, but since there is a certain amount of power associated with it, which is given by him this particular expression, we are going to have some coefficient outside it, because if you take a trace of this H Hermitian, it is the sum of the eigenvalues. So, sum of the diagonal elements over here would be zeta by m plus zeta by m times, which will be equal to zeta. So, this if I take the trace of it, I am going to get zeta upon m times, all of these are 1 m, which is zeta. So, this condition satisfies. So, only when there is a diagonal matrix and diagonal or identity matrix, and that is when H Hermitian is identity, that means H Hermitian identity would in other words mean that H is an orthogonal matrix. So, if this is an orthogonal matrix, then we can say that capacity is maximized, and then the expression of capacity can be, if we look at the inside term, log base 2 1 plus Es upon m times n naught. Okay. So, mt I have written as m, n naught, lambda I, they are all equal. So, that is zeta upon m. So, inside there is no dependence on this subindex I. So, therefore, this summation, each of the components of the summation are all the same, and therefore, we could simply write it is m times log base 2 1 plus Es by m times n naught m squared, or we could simply write it as C is equal to m log base 2 1 plus Es upon n naught m squared times zeta. Okay. So, one tiny step left after this, although we will move on to a new page with this. What we have is now, if we put the constraint, if we have mod or the mod squared of ij element of H squared to be 1, that means we are putting the constraint that each element of H has a power of unity, right. So, this would mean that Frobenius norm squared of H, which is sum of all of these values, and we have said initially that this is mt equals to mr equals to m. So, we have m squared such elements. So, this would be equal to m squared. So, we have said that this is indicated in our work by zeta, which is zeta is equal to m squared. So, if we use this result there, we are going to get we will be using zeta equals to m squared. So, zeta equals to m squared, this cancels out, we could write C is equal to m log base 2 1 plus Es by n naught. So, what do we have over here? This is a beautiful result that we have in front of us. This result tells us that the capacity, we could rather write it, this would be very useful, the capacity of an orthogonal MIMO channel. So, what is an orthogonal MIMO channel? An orthogonal MIMO channel is one where H Hermitian is identity and zeta upon m indicates the strength of the channel, where the total strength is zeta. So, that is what it is. So, if we could have taken this could be m or anything else, again the results would be the similar. So, this is the capacity of an orthogonal MIMO channel. M is m times the capacity of a seesaw channel. This is a wonderful result. So, look at the inside of it, log of 1 plus Es by n naught. This is the capacity of a seesaw channel, whereas since we have MIMO, we have m times the capacity of a seesaw channel. So, this is true when it is orthogonal, and to get an understanding what does it mean is that we have said H Hermitian is equal to some kind of an identity matrix. So, that means the components of H of the cross terms do not matter, they cancel out each other. So, components cancel out each other means that anything transmitted on this antenna is not reflected over there, because that you can clearly see when I write H Hermitian. If we take a small H1, H2, H11, H12, H21, H22 and multiply this by H11, H12 conjugate, H21 conjugate, H22 conjugate, you are going to get H11 squared plus H12 squared as the diagonal element. As the cross diagonal element, H11, H21 conjugate and H12, H22 conjugate. So, basically the cross terms cancel out, they are 0. So, there is no cross component. So, when you are transmitting H11, H12, H21, H22, S1, S2, you have H11, S1, H12, S2. So, when you transmit at the receiver, when you process it, that means I would multiply H Hermitian at the receiver for recovering it. This would result in an identity matrix, thereby indicating that S is decoded without having any influence of S2. So, this is the meaning of orthogonality, and we can also remember that when we talked about Alamuthi scheme, we said that the scheme basically orthogonalizes the channel. So, there also if you would have done H Hermitian H, you would have arrived at a diagonal or an identity matrix with a certain amount of power in that matrix, where non-diagonal elements are 0, indicating that signal transmitted in any one of the channel modes are not having any influence on any other of the received channel modes. So, this is very, very interesting and a very, very important result that we have arrived at for us to remember, and one of the most interesting things that we could have learned in this course is indicated in this particular expression. We will move on further in the next few lectures and talk about the capacity of MIMO channel when channel is known at the transmitter, then the effect of correlation. We have already studied correlation and would also look at a few other transmitter receiver architectures. Thank you.